All right, well, hello everyone, and welcome back. In today's video, we are going to introduce second-order circuits. Here's our goals for today's video. First, we will briefly review our procedure for first-order circuits with non-constant sources. You'll remember we covered this in our previous videos on first-order circuits. Once we're done with that last example, we're going to move on to second-order circuits. And you'll see that we'll apply a similar 10-step recipe for second-order circuits. And this 10-step recipe will help us write and solve differential equations for second-order circuits. So these are circuits containing one or more resistors and sources, but just two energy storage elements. And finally, we'll learn some shortcuts to help simplify the differential equations and make life a little bit easier. So let's start with a review of first-order circuits. And you'll remember that in order to solve a first-order circuit, we need to solve a first-order differential equation of the following form. So we need to solve dx dt plus ax of t equals f of t. And for this class, we consider three cases for RL and RC circuits. We consider the case where we have a unit step or constant source. We consider the case where we have an exponential source. And finally, we consider the case where we have sinusoidal sources. You'll also remember in our previous video, we introduced the unit step. And here, when we talk about unit steps and step sources, you'll remember what we're trying to do is we're trying to model sudden, constant changes in current or voltage. So the unit step is a way to mathematically model instantly flipping a switch or changing a voltage or current. You'll remember we defined the unit step function u of t to basically represent a function which is 0 for any time less than t naught. And then the function instantaneously hits the value 1 for time t is greater than t naught. And we can also write step functions where we have, for example, something like b u of t plus a, where in this case the value would be equal to a for time t less than t naught, and then it would be equal to a plus b for time t greater than t naught. So there's variations on the unit step function you see. In this case, it's actually u of t minus t naught plus a. That would be equal to a for time t less than t naught, a plus b for time t greater than t naught. And remember, of course, the value of the unit step function at that instant t naught is undefined. And most of the time in this class, we consider the case where the unit step function has t naught equal to 0, which just gives us u of t, which is 1 for t greater than 0 and 0 for t less than 0. All right, so now let's just briefly remind ourselves of our recipe for solving first-order circuits with non-constant sources. So in our previous video, we introduced this 10-step recipe, and you'll remember I mentioned that it's a lot of steps and a lot of different things to consider. But the advantage of following this recipe is that it guides you through the whole process of deriving that first-order differential equation and then solving it. So I know some students in this course have not yet taken differential equations class. So if you have not taken differential equations class yet, this is a good general approach to follow. And once you've taken differential equations, you may learn some additional strategies on how to solve these equations. You'll remember our strategy here is to first derive that differential equation. And once we've derived our differential equation, then we determine our natural response and our forced response. And so natural response we just determine based on the known form. Forced response we guess depending on our source type. And once we determine our natural and forced response, then we know our complete solution. The complete solution is just the sum of the natural and forced responses. Finally, we need to determine the constant k from our natural response, and we do that using the initial conditions that we find in our earlier step. So these problems will definitely appear intimidating at first. And my biggest piece of advice is to make sure you practice this recipe on your own. In our previous video, we did 2 examples of constant and exponential cases. And in today's video, we will do an example of the sinusoidal case. All right, so now that we have reviewed our recipe, let's go ahead and do one last example of first-order circuits with non-constant sources. And this time, we will illustrate how to solve the case for when you have a sinusoidal source. That brings us to our review question of the day. So, suppose we wanted to find the response Vc of t. That's the voltage across our capacitor here. So we want to find Vc of t for time t is greater than 0. We are told the initial voltage across that capacitor will be 0, and our current source outputs a sinusoidal function. We see we have 10 sine 2t u of t amps. So notice once again that if we write our current source as being current is 10 sine 2t u of t, what that means is, remember we have the u of t here. U of t is equal to 0 for time t less than 0, and u of t is equal to 1 for time t greater than 0. So at time t is less than 0, there is no current. But at time t is greater than 0, our current is given by 10 sine 2t. So this question has 2 parts. First, we are asked to show that the behavior will be represented by this differential equation. And once we've completed that part, then we need to determine natural, forced, and complete response for Vc of t. To solve this question, we basically need to follow all 10 steps of the recipe that we just covered. Let's go ahead and go through this step by step. Let's start with part A. We are told if we apply Kirchhoff's current law at the top node, show that the behavior of this circuit will be represented by 0.5 dVc dt plus Vc over 4 equals 10 sine 2t. Let's go ahead and apply Kirchhoff's current law. And in this case, I'm just going to label my currents so that I have our source current I1 entering the top node. And I'm going to assume that I2 and I3 are leaving the top node. Again, you can assume whatever directions you want as long as you are consistent with your sign conventions. So in this case, if I apply Kirchhoff's current law, I will have plus I1 entering, minus I2 leaving, and minus I3 leaving. And of course, my algebraic sum of currents entering and leaving must be 0. All right then, well, we need to get this equation in terms of only Vc of t and our current source. Because remember, our goal is to find that differential equation. So we need to get this equation in terms of only Vc of t and our current source 10 sine 2t. Well, we know that I1 is just going to be equal to 10 sine 2t because that is our current source. But notice I2 is going to be the current entering my capacitor. Let's call that IC of t. And then finally I3, well, that's the current flowing through my 4 ohm resistor. That's just going to be equal to, in this case, Vc of t divided by 4. Because notice my top node, if I put ground down here, my top node is sitting at a voltage of Vc of t. You might be wondering, well, how does that help us? Well, the term for I1 and I3 is good because we want everybody in terms of Vc and 10 sine 2t. We need to write IC of t in terms of Vc of t because we need our entire equation to be in terms of Vc. All right, so then how can we relate? How can we relate IC of t and Vc of t? Is there a tool in our toolbox that could help us here? How about this one? Recall that the current through our capacitor is equal to capacitance times dVc of t dt. So here again, IC is the current entering the positive terminal. So IC is equal to C dVc dt. So look what we can do. We can go ahead and substitute IC of t equals C dVc of t dt into our Kirchhoff's current law equation. And let's see what we get. Well, our I1 term is just 10 sine 2t, because that's the current entering through that path I1. So we have plus 10 sine 2t Remember, we're looking at time t is greater than 0, so we know that that current source must be powered on. Then I2, remember, we're subtracting. That's the current entering our capacitor. That is just going to be minus C dVc dt. And here, our capacitance C is just 0.5 farads. So we can go ahead and write this as 10 sine 2t minus 0.5 dVc of t dt. And finally, our last term, I3, well, that's just going to be minus 1/4 Vc of t, because current I3 must be our voltage Vc divided by 4 ohms, per node analysis rules. Notice this is looking awfully similar to our desired result. All we need to do is rearrange. So if we rearrange, notice I can move the negative terms to the opposite side, and I will end up with the desired result. I will have plus 0.5 dVc of t dt plus Vc of t divided by 4 equals 10 sine 2t. So you'll notice here, we went ahead and we've already completed the first few steps of our recipe. We have our initial condition, and we have our differential equation. So this is all the steps through step 5 are completed. So now that we've found this equation, we have finished the most challenging part of the question. Now, all that we need to do is solve. Our goal in part B is to follow the second half of our recipe to find natural response, forced response, and complete response. Let's go ahead and follow the recipe. So the last part of our recipe, if we follow our recipe, we need to get our equation in the desired form. So we need our differential equation to be in the form, you'll remember the form is dVc of t dt plus a Vc of t equals, in this case it'll be f of t, where that is our time-dependent source. Right now our equation is in a slightly different form. So currently, we have 0.5 dVc of t dt plus Vc of t divided by 4 equals 10 sine 2t. So let's multiply both sides by 2. And that will allow us to get our desired result. We want to get rid of that coefficient 0.5 in front of our derivative. So if we do that, we just multiply everybody by 2. So the 0.5 goes away. We get dvc of t dt. Vc over 4 multiplied by 2 becomes Vc of t divided by 2. That will equal 20 sine 2t. Because remember, we had to multiply everybody by 2 on both sides. So this is our first order differential equation in the desired form. Now we are ready to solve this equation following our recipe. Let's continue with step 6. To solve this equation, we first need to find the natural response. So we'll go ahead and follow step 6 through 10. Step 6 is to recognize that the natural response will have the following form. Natural response has the form, I'll call it Vc comma n of t. Natural response has the form k e to the minus at. And here we need to determine a. And that can be done using the Vc of t term of our differential equation. Or, of course, we know that a is related to our time constant tau. So we could also use our various equations. But here we can very quickly see from our differential equation, a is the coefficient on Vc of t. So here we can say a must be 1/2. That comes straight from the term in front of Vc of t. So here we have Vc of t divided by 2, which gives us 1/2. So therefore, our natural response for our equation will be k e to the minus 1/2 t. Remember, we will determine k later in step 9. So step 6 is complete. Let's move on to the next part. In step 7, we need to find our forced response. And here, we know that we have a sinusoidal source. So let's go ahead and guess from our table that our forced response Vc f of t will have the form a sine 2t plus b cosine 2t. All right, so now that we have this guess, we need to substitute into our differential equation, which you'll remember is given by dvc of t dt plus 1/2 Vc of t equals 20 sine 2t. So let's go ahead and substitute in. And so after substituting, we have d dt of our a sine 2t plus b cosine 2t. Then we have plus 1/2 a sine 2t plus b cosine 2t. And that whole thing must equal 20 sine 2t. So what we'll need to do here is combine like terms and use the comparing coefficients method to get an expression and basically get two equations, two unknowns, and solve for a and b. So if we go ahead and do that, we got to take our derivative. So derivative of sine gives us cosine. So this derivative term will be, 2 comes out, we'll have 2a cosine 2t. Then the b, of course, that b cosine 2t will become minus 2b sine 2t. And then the next expression, we just multiply 1/2 through. So we have plus 1/2 a sine 2t plus 1/2 b cosine 2t. And all that stuff must equal 20 sine 2t. And I'm also going to add the term 0 cosine 2t. This will, once again, since there is no cosine term, but if we add this, it lets us compare coefficients. So let's go ahead and combine like terms. And we will see that we get the following. We get negative 2b plus 1/2 a sine 2t plus 2a plus 1/2 b cosine 2t equals 20 sine 2t plus 0 cosine 2t. And look what happens. So here we determine, by comparing coefficients, we can say that negative 2b plus 1/2 a equals 20. And we can also say that 2a plus 1/2 b equals 0. So if we use a solver, such as Wolfram or your preferred equation solver of choice, you'll determine that a must equal 40 over 17, and b will be negative 160 over 17. And therefore, after that extra comparing coefficients, we can determine our forced response VC of t must be equal to 40 over 17 sine 2t minus 160 divided by 17 cosine 2t. Believe it or not, we are now almost finished with this question. Now that we have found both our forced response and our natural response, we can determine our complete solution. So in step 9 of our recipe, we can determine our complete solution by adding the natural and forced responses. And we determine, in this case, that Vc of t, our complete response, will be equal to ke to the minus 1/2 t plus 40 over 17 sine 2t minus 160 over 17 cosine 2t. Lastly, we just need to plug in our initial condition to find k. And we know that our initial condition was given to us as Vc of 0 equals 0 volts. So if we go ahead and plug that in, we can say that 0 must equal ke to the minus 1/2 times 0 plus 40 over 17 sine of 2 times 0 minus 160 over 17 cosine of 2 times 0. So if we go ahead and simplify that, we end up with k, so that becomes 1. Sine of 0 becomes 0, so this whole term vanishes. And this term becomes 1. So we have k plus 0 minus 160 over 17 must all equal 0. That gives us k must equal 160 over 17. And finally, our complete response and our final solution will be Vc of t equals 160 over 17 e to the minus 1/2 t plus 40 over 17 sine of 2t minus 160 over 17 cosine 2t. So there you have it. There's a lot of steps here, and there's definitely multiple areas where you need to be careful of substituting properly and following the correct procedure. But at the end of the day, these questions aren't so bad once you get the hang of the steps. So please make sure you go back through this example and practice it on your own. Make sure you're familiar with the procedures for finding the differential equation, the natural response, and the forced response. Once you've done this recipe a few times on your own, these questions will be a lot more straightforward. Feel free to reach out if you have further questions on this. So this concludes our discussion of first-order circuits, and we have now done an example of the different cases with step source, exponential source, and sinusoidal source. So let's now turn our attention to second-order circuits. So when we talk about second-order circuits, these are circuits which contain not one, but two energy storage elements. So first-order circuits had just one inductor or capacitor, but second-order circuits contain a total of either two inductors or two capacitors, or one inductor and one capacitor. So second-order circuits are called second-order circuits because they can be represented by a second-order ordinary differential equation. Most of the time, we deal with circuits that contain a resistor, inductor, and capacitor, so we call them RLC circuits. But we'll see that the behavior for a second-order circuit will always have the form of this second-order differential equation. Once again, you'll notice that I have written this equation as a very general form, where here x of t could be a current or a voltage. So depending on what you're interested in, the x of t is current or voltage as a function of time, and f of t is the time-dependent input applied to the circuit. So as you've seen, the order of the differential equation is ultimately equal to the number of capacitors and/or inductors in that fully simplified circuit. So you might be wondering, well, why would we bother with these second-order circuits? I mean, second-order differential equations can be pretty ugly. But these actually are used in many, many applications. Very commonly, RLC circuits are used in communications, precise instrumentation, and basically any time we want to filter or process a signal. A good example of this is if you have a radio antenna, and you want that radio antenna to receive signals only at certain frequencies. So as engineers, there's definitely going to be situations where we need to be able to control the behavior of RLC circuits and second-order circuits, because we need the circuits to help us do useful stuff. So let's briefly review some key terms here. As we mentioned, the second-order circuits are represented by a second-order ordinary differential equation. But these terms have some important names and important properties. You'll remember f of t, we often call it the input signal or the forcing function. That is the term that captures time-dependent sources and inputs in that second-order circuit. X of t is the full solution of our second-order circuit. So that's generally our voltage or current as a function of time. And we often call this our complete response. It's given by the sum of our natural response and our forced response. Once again, natural response is the solution to our differential equation when our forcing function is 0. And forced response is our solution when f of t is not equal to 0. So we'll apply a similar strategy as we learned, where in order to solve these second-order differential equations, we must find both the natural and the forced response and sum them to get our complete response. All right, couple more key terms. So that x of t, we called that our complete solution. Remember, x of t is also equivalent to our output current or voltage that is produced by our second-order circuit. And so sometimes we call it our response for that circuit. Notice there's also these very important terms here. There is a term called alpha. Alpha is called the damping coefficient. And we'll talk more about what that is in just a moment. But this is a very important term. And then there's also this other term called omega naught. That is called the resonant frequency of our second-order circuit. We'll return to these in just a moment, but you'll see these are very important terms that influence the behavior. So you'll notice that I mentioned there was that term called resonant frequency. And so what we're actually talking about here is we're talking about circuits that can actually oscillate, or that can actually have some electrons resonating in them at a certain frequency. So the behavior of these second-order circuits is very similar to a mechanical spring. In physics, we often call these second-order circuits, or similar things with this behavior, a harmonic oscillator. You may have experienced similar behavior if you've played with a spring before, or if you've ridden in a bumpy vehicle that needs its shock absorbers replaced. This phenomena, where circuits or springs vibrate or oscillate at given frequencies, it's called damped harmonic motion. And this behavior is actually seen in many areas of science and engineering. And so it turns out that these second-order circuits and RLC circuits, mathematically, the oscillating behavior we see is the same behavior, mathematically, as a bouncing spring. So believe it or not, there's actually a really nice mechanical analogy between bouncing springs and second-order circuits. Notice that for a spring, if we change the position of the spring or displace it, that will cause the spring to bounce. Similarly, a change in voltage or current, such as powering on a source, that can make our circuit oscillate. So again, it goes back to the external force, just like an applied voltage or current may cause our circuit to oscillate. Next, we see a spring can store potential energy as it moves around, and a capacitor can do a similar thing. Also, in a spring, we have friction that dampens the motion, and that behaves very similarly as a resistor, which dissipates current and voltage in our circuit. Finally, in a spring, we have a mass that's hanging off the end of it in order to stretch the spring. And electrically, the inductor has a similar behavior, where it helps store some potential energy, in this case, magnetic energy. So this might seem a little bit strange to visualize. Let's take a look at a simulation. So this is actually a simulation from Fallstad.com, which has a really nice simulator. And look what's happening here. When I start the simulation, you can see that initially the little yellow dots, that's our current inside our circuit, initially it bounces a lot and it's moving around. But over time, the oscillations stop. And so we can see that basically when I start the simulation, a 5-volt DC voltage is applied. And so what we get is we get a sudden a sudden disturbance causing the current to oscillate, as shown in this behavior. And we can see the current is actually flowing back and forth, until eventually it stabilizes. So that's why we call this behavior damped harmonic motion or an oscillating circuit, because the current is actually moving back and forth, and eventually returning to a stable value. So it turns out that these second-order circuits can have three possible types of oscillations. So the first case is where we have what's called overdamped behavior. You can see the overdamped behavior as the red dashed line in this plot. When we have overdamped behavior, the circuit is going to exponentially return to equilibrium without any sort of oscillations or back and forth motion of current or voltage. So you see in the red dashed line, we just simply return straight to equilibrium. There's no oscillating positive negative of our signal. Second case is what's called critically damped. And in critically damped behavior, you see that we return to equilibrium exponentially, but we do so as quickly as possible. And there's no oscillations. So often in engineering, we want RLC circuits to operate at critically damped behavior. That will allow our circuits to return to equilibrium very quickly, and it will minimize possible error or noise in our signals. The last case shown here is called underdamped behavior. And underdamped is the behavior we saw in the simulation on the previous slide. In underdamped behavior, we basically oscillate slowly up and down until we gradually decrease our amplitude of each oscillation to 0. So these are the three potential cases that we will work with when we deal with RLC circuits. So how do we know what behavior we're going to get? How can we predict and control this behavior? So it turns out, mathematically, we can show that the behavior of that natural response, the behavior of our second-order circuit, it basically depends on that damping coefficient alpha and the resonant frequency omega naught. Remember, those were the two coefficients in front of some of the terms in our second-order differential equation. So it turns out if our damping coefficient alpha is greater than the resonant frequency omega, that means that the desire to suppress the oscillations is stronger than the oscillating force. So we end up with overdamped behavior because that damping coefficient overpowers the resonant frequency. If our damping coefficient is exactly equal to resonant frequency omega naught, then we have the critically damped case. Often this is our design target, because when we're critically damped, we return to equilibrium as quickly as possible. And finally, if we see that our damping coefficient is less than the resonant frequency, then that means that the damping coefficient is not strong enough to prevent oscillation. And we see that we end up with the underdamped case, and our behavior is quite a bit more complex for our natural response. We see that we have the square root of -1 involved in our solution and some imaginary terms. These terms are needed in order to produce that underdamped oscillating curve. So just for fun, I show on the next slides how to derive these behaviors. You may learn more about this when you take differential equations class. For the purpose of this course, I do not expect you to know the derivation of these behaviors, but I do expect that you know how to use the recipe in the slides later on. So again, this derivation is just for your information. I'm not going to put this on exams. But you can see that you'll maybe learn in differential equations class that you can assume the solution of this equation will have the form of an exponential term. And if we substitute that in, you can end up with some sort of quadratic relationship here. And we can use the quadratic formula to basically derive some expressions relating our damping coefficient and resonant frequency. And then using these expressions from our quadratic formula, we can identify those three possible cases for overdamped, critically damped, and underdamped. So I do not expect you to know these derivations for this class, but it may come up later when you take differential equations. All right, so these second-order differential equations, they can look kind of intimidating at first. But there's some good news. The good news is that the hardest part of solving these second-order circuits is actually just identifying the differential equation we need to solve. Once we've found out and derived what our equation is, it's actually pretty straightforward to solve these differential equations. And so it turns out that once again, the smart mathematicians have done a lot of the heavy lifting for us. And we're going to learn some shortcuts we can use to help us solve those second-order circuits. So now let's go ahead and introduce a new recipe that will help us solve second-order circuits more efficiently. So once again, I highly recommend that you add this recipe to your toolbox and practice our examples on your own to get comfortable with it. And so this recipe is quite similar to our first-order circuit recipe. We first verify that we do indeed have a second-order circuit, and we find initial conditions. Notice that we need two initial conditions in this case because we have a second-order differential equation. Then, just like before, using Kirchhoff's laws, we need to derive that differential equation in the desired form. Often it's also helpful to have our inductor and capacitor tools as well. So often you need those derivative relationships and integral relationships when deriving the differential equation. Once you have that differential equation, you can directly determine alpha and omega naught from your differential equation. So you can just look at the coefficients to determine alpha and omega naught. And you want to be careful of units here. Just make sure if you're substituting any units, watch out for ohms, kiloohms, farads, millihenries. Make sure everything is in ohms, farads, amperes, and volts. Once you have found alpha and omega naught, you can then determine what we call our roots, S1 and S2. And as you can see, the roots are given by these quadratic expressions. And once you have determined alpha, omega naught, and our roots, you can find our natural response. The natural response depends on the relative values of alpha and omega naught. We see that if our alpha value is larger, then we get that overdamped behavior, and we get the form of our natural response. If we're critically damped, notice that our natural response will be different. And that, again, comes from the fact that alpha and omega naught are equal for critically damped. Finally, if alpha is less than omega naught, then we get the underdamped behavior, and our natural response will have some imaginary terms in it. So here you would need to calculate this omega sub n and use j as the square root of -1. Once you have found your natural response, then you just guess the forced response. And remember, once again, we can use the same guesses as we did with first-order circuits. So you can guess the form of your forced response and take your guess and substitute that guess back in to your differential equation that you determined in step 3. Finally, you take your natural and forced response and add them to get your complete response. The very last step, just like before, is to use initial conditions to determine any remaining constants in your natural response. So that's basically it. You find your complete response, and if there's any additional unknowns, you solve for those in the very last step. Once again, this recipe might look a little bit intimidating. It's certainly a bit more time-consuming than some of our other problems. But please practice this example on your own and follow along with our next few examples. Once you've gone through this recipe a few times on your own, it'll make a lot more sense, and it'll be a lot more comfortable. So with that, let's go ahead and start with our first example. Here we're given a second-order circuit. We're given some initial conditions, and we're being asked to determine a second initial condition for di dt at time t equals 0. And then we're asked to derive a second-order differential equation for our circuit and show that we end up with this result. Let's go ahead and follow the first part of our recipe in order to complete this example. So first, our goal is to determine a second initial condition for di dt at time t equals 0. So notice we have a very nice loop circuit here. Let's go ahead and take a moment to look at what we have. So basically, we know we have some source v of t. We have our inductor L, say with voltage VL across it. We have a resistor R. There would be some voltage drop VR across our resistor. And then we have our capacitor with capacitance C. And then, of course, we're trying to find that initial condition for di of t dt. So let's go ahead and first consider what we know. At t equals 0, we know that v of t is 0 and I of t is 0. Well, if our current is 0, then our voltage across our resistor must also equal 0. We're also given in our question that we know in this case, we're just given the information that Vc is equal to 5 volts. So we're given that. We don't yet know anything about VL. But we want to find a second initial condition for di of t dt. Our next step would be to find some way to relate all of the values in this circuit. Let's apply Kirchhoff's voltage law. If I apply Kirchhoff's voltage law and walk around my circuit in the direction of I of t, I determine that plus V of t minus VL minus VR minus Vc must be 0. And we already concluded that we know 3 of the terms. Here, the only term we don't know is VL of t. We want an expression for di of t dt. How is VL of t related to di of t dt? Notice that the current through my inductor is the same as the current through my whole circuit in this case. And from our toolbox, we know that VL of t is just going to be equal to L times di of t dt. So if we substitute into Kirchhoff's voltage law, we determine that negative L di of t dt minus 5 volts equals 0. So if we solve, we determine that di of t dt will be equal to negative 5 over L at time t equals 0. So notice how using Kirchhoff's voltage law helped us come up with the extra initial condition. So if you ever need to derive an extra initial condition, often Kirchhoff's laws and our inductor and capacitor tools can be really helpful here. Let's move on to the next part. In part B of this question, we are asked to find the second order differential equation for I of t in terms of RLC and V of t. And we should end up with the answer shown. Well, in this case, our goal is to get an equation for all the elements in the circuit in terms of I of t. So we want to remember when writing our equation here, we want to try to get an equation with all the terms in terms of I of t and our voltage source V of t. So here you want to ask yourself, how can we relate V of t and I of t in our given circuit? Well, we have a convenient loop, so let's try applying Kirchhoff's voltage law again. So here, if I once again walk around my circuit and apply Kirchhoff's voltage law, I know that plus V of t minus VL of t, I'm just assigning polarity in the direction that my current is traveling. So I have plus V of t minus VL of t minus VR of t minus VC of t equals 0. So how do we relate each of these terms to I of t? Remember, our goal is to get all of the terms of this equation in terms of I of t and V of t. Well, what do we know? Well, we know VR of t is equal to our resistance R times I of t. So that can relate VR to current. What else do we know? Well, we know VL of t, that's just going to be equal to L times di of t dt, because I of t is the current passing through our inductor. How about the voltage of our capacitor? Well, we know that we have that integral equation. And so in this case, notice we can actually use the integral here to help us find our capacitor voltage in terms of I of t. So we can substitute each of these terms back in to Kirchhoff's voltage law. So we have an equation here, but it's got an integral in it. How can we get rid of that integral? How about we take the derivative? So we'll take the derivative of both sides of our equation. So if we do that, notice what we get. So here, our voltage gets the derivative taken. Derivative of L di dt becomes L second derivative of I of t. Then we get resistance times the first derivative. And then we have 1 over c times I of t. Notice now we're starting to look like a second order differential equation. If we rearrange, you can see that we can get something pretty close to our desired form. I'm going to move all the negative terms to the right-hand side, keep dv dt on the left, and then, of course, we can show that we have L di dt squared plus R di dt minus 1 over c I of t equals derivative of our voltage. But notice we need to divide by L to get the equation in the desired form. And if we do that, we get our desired result. So we end up with d squared I of t dt squared plus r over L di of t dt minus 1 over LC I of t equals 1 over L dv dt. So this is an example of how you would actually derive that second order ordinary differential equation for a given circuit. All right, so now let's go ahead and look at the second half of our recipe. So now we have a similar circuit as we were looking at before, but now we're given some more information about it. Here we're being asked to determine the complete response for I of t, and we're given some information here. We're told about the inductance, resistance, and capacitance, and we are also given an exponential voltage source, and we are given some initial conditions. So here we need to use the second half of our recipe, and we can use the equation in example 1 to help us solve. So let's go ahead and give this one a try. And so we already know from our earlier example, we know the expected form of this differential equation. We know that the differential equation will be of the form we have d squared I of t dt squared plus r over L di of t dt plus 1 over LC I of t equals 1 over L times dv of t dt. So here we can go ahead and substitute the given values. Because remember, we are given, in this case, we have L is 2 henries, R is 200 ohms, C is 200 times 10 to the minus 6 farads, and V of t is 50 e to the minus 2t for time t is greater than 0. So let's go ahead and substitute everybody in. And if we do that, we will end up with the following. So R divided by L, that's 200 divided by 2, that gives us 100 di of t dt. And 1 over LC is 1 over 2 times 200 times 10 to the minus 6. So if we math that through, that gives us 2500 I of t. And that whole thing will be equal to 1 over L, so that's 1/2 of d dt of 50 e to the minus 2t. So this whole thing is our differential equation from step 3. Let's continue with step 4 of our recipe. In step 4, we need to find alpha and omega naught using the differential equation. So here, we know that 100 is going to be 2 alpha, and 2500 is omega naught squared. So 2 alpha is 100, omega naught squared is 2500. Therefore, we can determine, in this case, that alpha is 50 and omega naught is square root of 2500, or 50. So that concludes step 4. In step 5, we need to find our roots, which are S1 and S2. And we know in our recipe, S1 is equal to negative alpha plus square root of alpha squared minus omega naught squared. S2 is equal to negative alpha minus square root of alpha squared minus omega naught squared. Here, notice both alpha and omega naught are 50. And so if we go ahead and plug those in, we determine that S1 is going to be negative 50 plus 0, or 50. And S2 is also going to be negative 50 minus 0, or 50. So in step 6 of our recipe, we use S1 and S2 to determine our natural response. So here, S1 is equal to S2. Oops, and I miswrote. These are both negative 50. So we are critically damped. And based on this, the natural response for a critically damped second order circuit, I'll call it IN of t in this case, is e to the minus s1t, which is e to the minus 50t, times k1t plus k2. So k1 and k2 are constants that will be found later. So we'll determine those in step 9. All right, so we found our natural response. Next step is to find the forced response. So this is step 7 of our recipe. So here we have an exponential source. So let's guess for an exponential source. We want to guess that our forced response, IF of t, is going to be equal to n e to the minus 2t. So then we need to substitute We're going to substitute that forced response into our differential equation. And then we're going to compare coefficients to find n. If we do that, we get the following. Notice I'm just substituting in for each I of t term. So I have second derivative of n e to the minus 2t, plus we have 100 times our first derivative, n e to the minus 2t, plus 2500 times just I of t, which is n e to the minus 2t here. And all of that must equal the right-hand side of our equation, which we had here, 1/2 times 50 e to the minus 2t. Derivative of this is actually going to be negative 1/2 times 2 times 50, or just negative 50 e to the 2t. I'm sorry, negative 50 e to the negative 2t. So we have that as the right-hand side. So here we go ahead and take our derivatives, and doing that gives us 4n plus negative 200n plus 2500n e to the negative 2t equals negative 50 e to the negative 2t. So we determine if we combine like terms, compare coefficients, we have 2300 for n equals negative 50. That means n is approximately negative 0.0217. That gives us our forced response will be equal to negative 0.0217 e to the negative 2t. And believe it or not, we are just about finished. Our complete response is the sum of the natural and forced response. So here we determine that our I of t is in of t plus if of t, or if we substitute in, that is e to the minus 50t times k1t plus k2, and then minus our forced response, which is 0.0217 e to the minus 2t. Our last step is to plug in the initial conditions. And we know our initial conditions were given to us. We have I of 0 is 0 amps. That gives us, if we plug it in, we have 0 must equal e to the negative 50 times 0 times k1 times 0 plus k2 minus 0.0217 e to the negative 2 times 0. So if we substitute that in, we'll determine that k2 must equal positive 0.0217. We use our second initial condition to find k1. So we have di of 0 dt equals 0. So here we need to use the product rule and take our derivative. So we take the derivative of e to the minus 50t times k1t plus k2. You might find it helpful to review the product rule from calculus class as you do that derivative. Basically, product rule says that the derivative of the product of two things is the derivative of the first times the second plus the derivative of the second times the first. So if we use product rule, we get negative 50 e to the minus 50t times k1t plus k2 plus, now we take the derivative of our second term, which is k1 times e to the minus 50t for our second term. And of course, the derivative of our forced response here, we add that in as well. And so we go ahead and we substitute everything in, and notice because time t equals 0, a lot of these terms will disappear. So here we just need to solve for k1. So we end up with, we have negative 50 times k2 . So here we determine negative 1.085 plus k1 plus 0.0434 equals 0. k1 must equal 1.0416. So we plug in k1 is 1.0416. 1.0416t, and then we have plus k2, which again, k2 was 0.0217, and then that all that stuff is minus 0.0217 e to the minus 2t. So there you have it. We first found our natural response, then our forced response, and we substitute those together to finally determine the complete response. I highly recommend going back through this example, and please verify that you're able to get the same result. These problems may seem a bit tricky at first, but as you go through examples, you'll get more comfortable. And we'll continue to do some additional examples in our next video. So please do take the time to review this video and our next video very carefully to get comfortable with these topics. All right, so now you should be more comfortable with solving our first order circuits as well as second order circuits. Please make sure that you keep the tools we've covered handy and practice them so that you know how to write and solve differential equations for second order circuits. Also, definitely keep all the different toolbox equations we've covered handy. You'll definitely want to use Kirchhoff's laws and our inductor and capacitor equations to help simplify. And I think you will find that our 10-step recipes are very useful shortcuts to guide you through the process and make solving these equations easier. Feel free to reach out if you have any further questions, and we'll see you in the next video.